When we classified the different substances as electrical conductors and insulators, we did so in reference to the atomic or molecular structure of materials. Therefore, the interpretation of the result of the previous experiments using a charged capacitor with a vacuum or a dielectric between the plates, is based on the atomic and molecular nature of insulating materials. In order to give the interpretation of the behavior of dielectrics in an electric field, we start with more general results obtained from the empirical data related to the electrical insulators. These results tell us that the majority of dielectrics can be classified into two different groups, according to whether the atoms and molecules that make them up have an electric dipole moment or not without an external electric field. Some of the dielectrics are called nonpolar dielectrics since they consist of nonpolar molecules in which the time-averaged centers of gravity of the positive and negative charges coincide without an external electric field, that is, these type of insulating materials do not have an electric dipole moment. However, in an external electric field the positive charges are shifted in the direction of the field, and the negative charges are shifted in the opposite direction within these nonpolar molecules. As a result of the displacement of the two types of charge in opposite directions, they become an electric dipole, that is, the molecules acquire an induced dipole moment. Other dielectrics are known as polar dielectrics since they are made up of polar molecules that have a permanent electric dipole moment even without an external electric field, as a consequence of their internal structure. In the absence of an external electric field, these polar or dipole molecules with a constant dipole moment are completely disoriented due to their thermal motion. However, under the influence of an external field, they align their axis in the direction of the electric field to a lesser or greater extent. We can also give some examples for both nonpolar and polar dielectrics. The most common examples for nonpolar dielectrics are hydrogen or oxygen, or more generally symmetric diatomic gases or hydrocarbons, but we can also mention rubber, Teflon and paraffin wax. The key examples for polar dielectrics include water, hydrogen chloride, alcohol, and polyvinyl chloride. We note that there are some insulators that are polarized in a different way than polar and nonpolar dielectrics. For example, in the case of a salt crystal, two lattices of positive sodium ions and negative chloride ions are shifted relative to each other by half a unit cell dimension along a crystal axis, and form the crystal lattice of sodium chloride. Then the polarization of a salt crystal can be interpreted as the two lattices become slightly displaced from their equilibrium positions relative to one another in an external electric field. The polarization of insulators is similar to the influence in conductors, but there is a significant difference between them. While in the case of influence, the two types of charge can be separated by dividing the conductor into two parts, this is not possible for polarized insulators, because any infinitesimal volume element of an insulator contains an equal amount of the two types of charges. Based on this explanation of the behavior of insulating materials, the same conclusion is reached for both the types of dielectrics applied in the experiment for a charged capacitor. The dielectric placed in the electric field E0 due to the charges plus Q and minus Q on the metal plates of the capacitor remains neutral as a whole, but dipole chains form inside the insulating material and polarization charges appear on its surface. The negative charges minus Q' are induced on the surface of the dielectric adjacent to the plate with the charge of plus Q, whereas the positive charges plus Q' are induced on the surface of the dielectric adjacent to the plate with the charge of minus Q. The volume electric charge density is zero everywhere inside the polarized homogeneous dielectric, because the algebraic sum of the opposite charges in the dipoles chains vanishes. Due to the presence of induced or polarization charges, some amount of the field lines of the electric field E0 start from the induced charges plus Q' and end on the induced charges minus Q'. As a result of polarization, the density of the electric field lines or the electric field strength will be less inside the dielectric material than in a vacuum between the plates with the same charges plus Q and minus Q. At the same time, the lower field strength corresponds to a lower voltage and a greater capacitance of the capacitor, in agreement with the result obtained in the first experiment. The electric field strength E inside the dielectric can be considered as the vector sum of the electric field strength E0 due to the charges plus Q and minus Q on the plates of the capacitor, and the electric field strength E' due to the charges plus Q' and minus Q' induced on the boundary surfaces of the dielectric. Since the vector E' points in the opposite direction to the vector E0, the magnitude of the vector E is equal to the difference between the magnitudes of the vectors E0 and E'. As shown in the previous experiments with a charged capacitor, the magnitude of the field strength E is given by the ratio of the magnitude of the field strength E0 to the relative permittivity εr of the dielectric inserted between the plates of the capacitor. If we substitute this expression into the left-hand side of the equation, Then we can express the magnitude of the electric field strength E prime by the magnitude of the electric field strength E naught, times 1 minus 1 over epsilon r. Because the relative dielectric constant epsilon r is always greater than 1 and it has a finite value, these equations express the fact that the electric field strength inside dielectrics is always less than the electric field strength of a capacitor with a vacuum or air between the plates, and it is always greater than 0. The charges plus Q' and minus Q' induced on the surface of the polarized insulating material that produces the electric field E' are also known as polarization charges, whereas the charges plus Q and minus Q producing the electric field E naught between the plates of the capacitor are called real charges. The difference between the real and polarization charges producing the electric field E and the dielectric are called free charges as well. We can also derive the relation between the polarization charges Q' induced on the surface of the dielectric and the real charges Q, and find that Q' is equal to Q times 1 minus 1 over epsilon r. If sigma is the surface charge density of the real charge Q over the plates of the capacitor with the area A, then the polarization surface charge density sigma prime of the polarization charge Q' is simply equal to sigma times 1 minus 1 over epsilon r. When we studied charged conducting surfaces, we found that the electric surface charge density sigma of two uniformly charged parallel infinite conducting planes is equal to the product of the vacuum permittivity epsilon naught, and the magnitude of the electric field E naught due to the surface charge distributed over the planes. Here we can apply this finding since it is a good approximation for the uniform electric field between the plates of a capacitor. We also saw that the magnitude of the electric field E naught for a vacuum or air between the plates is given by the relative permittivity epsilon r of the dielectric between the plates, times the magnitude of the electric field E for the dielectric between the plates. By inserting this result into the equation describing the polarization surface charge density, we can write sigma prime as the vacuum permittivity epsilon naught, times the relative permittivity epsilon r minus 1, times the magnitude of the electric field E between the plates of the capacitor. We saw that in a dielectric that has become polarized in an external electric field, atoms or molecules develop or align their electric dipole moment in the direction of the field. The degree of the polarization of an insulating material in an electric field is characterized by the electric dipole moment of the material per unit volume, and it is called the electric polarization P of the dielectric. If an isotropic dielectric is placed in the uniform electric field of a parallel plate capacitor, then it becomes uniformly polarized, where the polarization charges plus Q' and minus Q' induced on the surfaces of the dielectric at a distance d from each other produce a dipole moment of the dielectric. The electric dipole moment P' of the polarized insulating material completely filling the space between the plates of the capacitor, is given by the product of the polarization charge Q' and the distance d of the two surfaces of the material at the plates. Here we express the polarization charge Q' by the polarization surface charge density sigma prime times the area A of the plates of the capacitor. Because the product of the area A of the plates and the distance d gives the volume V of the dielectric inserted in the space between the plates, we can write the dipole moment P' as the product of the surface charge density sigma prime and the volume V. Hence the polarization P of the dielectric defined by the ratio of the dipole moment P' of the insulating material to its volume V, is equal to the polarization surface charge density sigma prime of the dielectric. This result shows that the polarization has the same unit as the surface charge density, and it measured in coulomb per square meter if we use SI units. If we consider the electrical polarization P as a vector pointing from the negative polarization charge minus Q' to the positive polarization charge plus Q', then we can write the electrical polarization P of a dielectric as the polarization dipole moment P' of the dielectric divided by its volume V. If the electric field is not uniform or the dielectric is inhomogeneous, then the polarization P of the dielectric will be different at different points of the dielectric. In this case we need to consider a volume element delta V of the dielectric at any given point that is small enough to allow us to assume that any macroscopic property of the insulating material, such as density, temperature, or electric field strength is constant in the volume element. At the same time delta V must be big enough to contain many molecules with electric dipole moment. We can add these dipole moments P'I for all the n molecules in the volume element and divide this sum by delta V, which gives the electric polarization P at the given point of the dielectric polarized in an electric field. If the volume element delta V becomes an infinitesimally small volume element, then we can formally define the polarization P of a dielectric with the electric dipole moment P' by the derivative of the electric dipole moment P' with respect to the volume V. We however saw that there is a finite number of electric dipoles in any volume element, that is the dipole moment in a polarized insulator has a discrete nature. The derivative of such a quantity can still be determined in a macroscopic approach, where we consider the electric dipole moment as a quasi-continuous vector field in dielectrics. We already saw that the magnitude of the polarization in a dielectric filling the space between the plates of a charged parallel plate capacitor is equal to the polarization surface charge density of the insulating material. Now we examine the relationship between polarization and polarization surface charge density in a more general situation. Let us place an oblique rectangular prism made of a homogeneous isotropic dielectric into a uniform electric field parallel with the lateral faces of the prism, as seen in the figure. Here the length of the lateral edges is denoted by L, and A is the area of the bases of the oblique prism parallel to each other. In the electric field, polarization charges appear over the boundaries of the bases that can be described by the sigma prime surface charge density. Since the displacement of charges inside the dielectric occurs parallel with the lateral faces of the oblique prism, no polarization charges are induced over the surface boundaries of these faces. The dielectric acquires a dipole moment due to polarization, which is equal to the amount of polarization charges on the boundary of the bases, times the distance between the two bases measured along the direction of the displacement of the charges in the dielectric, that is along the lateral faces of the oblique prism. Then the dipole moment P' of the dielectric is equal to the product of the polarization surface density sigma prime and the area A of each base, times the distance vector d with the length L of the lateral edges pointing from the negative polarization charges to the positive ones. By applying these notations, we can write the polarization capital P of the dielectric given by the dipole moment P' over the volume V of the dielectric, as sigma prime times A over V, times the vector d. If n is the unit normal vector to the base with positive induced charges pointing outward, then the volume V of the oblique prism can be expressed by the dot product of the vectors d and n, times the area A of the base. By substituting this formula into the equation obtained for the polarization capital P, the latter reduces to sigma prime over the dot product of the vectors d and n, times the vector d. Now we take the dot product of the result with the unit normal n, which gives the polarization surface charge density sigma over the bases of the oblique prism as the dot product of the polarization capital P of the dielectric, and the outward pointing unit normal n to the base with positive induced charges. That is sigma prime is equal to the normal component of the polarization capital P of the dielectric with respect to the surface of the dielectric. If the dielectric material has a shape of a cuboid, then the polarization and the normal vector to the base become parallel, and we regain the equation stating that the polarized surface charge density is given by the magnitude of the polarization. The expression derived above also holds for the opposite base of the oblique prism with negative charges, since then the unit normal n to that base points in the opposite direction, and thus the normal component of the polarization capital P is negative. This expression is also valid for the lateral faces of the oblique prism where the polarization surface charge density vanishes, because the normal vectors to the lateral faces are perpendicular to the polarization vector of the dielectric. As a result, we have obtained a general formula describing the polarization surface charge density of dielectrics. According to this equation, the normal component of the polarization capital P represents the amount of charge that is displaced across the unit surface area in the direction of the unit normal n. This interpretation can also be applied in the case of inhomogeneous polarization, where the magnitude and the direction of the vector capital P vary at different points in the dielectric. In order to be convinced of this statement, it is enough to think that the dielectric is divided to small volumes within which the polarization can be considered homogeneous. We also mention that the quantities related to electric polarization, such as the polarization surface charge density sigma prime describing the distribution of the polarization charge q prime, are normally distinguished by the subscript p instead of using the superscript prime. Then we can write that sigma p is equal to the dot product of the polarization capital P and the unit surface normal n. This more frequent notation will be applied here as we talk polarization charges distributed in a spatial volume. In the case of inhomogeneous polarization, polarization charges appear not only on the surface of the dielectric but they are also distributed throughout the volume of the insulating material. In order to determine the density of the volume polarization charges in the dielectric, we consider an arbitrary volume V within it enclosed by the surface S. The amount of charge that is displaced across the surface element ds of the boundary surface S in the direction opposite to the outward pointing unit normal n to the surface element, is given by the negative dot product of the polarization capital P and the volume V and the unit normal n, times the surface area ds. This expression can also be written as the negative dot product of the polarization capital P and the surface element vector ds with the area of the surface element and the direction of the unit normal n. If we integrate this expression over the whole boundary surface, then we obtain the total amount of polarization charges QP displaced across the boundary surface S of the volume V, that is QP is given by the negative surface integral of the normal component of the polarization P over the surface S, or the negative surface integral of the dot product of the polarization P and the surface element vector ds over the surface S. Here the minus sign indicates that the polarization charges are displaced from outside into the volume V in the direction opposite to the surface normal N. Now we introduce the polarization volume charge density ρP such that its volume integral over the volume V gives the total amount of the polarization charge QP displaced into the volume V. By comparing the two equations describing the volumetric polarization charge with each other, we can write that the volume integral of the polarization volume charge density ρP over the volume V is equal to the negative surface integral of the polarization P over the boundary surface S of the volume V. If we apply Gauss's divergence theorem, then the surface integral in the right-hand side of the equation can be transformed into the volume integral of the divergence of the polarization P over the volume V. Because this equation holds for any arbitrarily volume V in the dielectric, it must be valid at any point in the insulating material, and we conclude that the polarization volume charge density ρP in a dielectric is equal to the negative divergence of its polarization P. For a uniformly polarized dielectric, we immediately see the divergence of the polarization vanishes and the polarization volume charge density ρP is equal to 0, that is, there is no polarization charge inside the insulating material, as we expected. This result indicates that together, the polarization surface charge density and the polarization volume charge density represent the polarization charges induced in dielectrics. Hence, three equations describe the polarization vector field in an insulating material under the influence of an external electric field. The first one tells us that the polarization surface charge density sigma p at any point of the boundary of the dielectric is equal to the dot product of the polarization P and the unit surface normal n at the given point. The second one states that the volume charge density at any point inside the dielectric is given by the negative divergence of the polarization P. The last one is the obvious requirement for the vanishing polarization P outside the insulating material. We note that the three equations do not uniquely determine the polarization vector field in the dielectric, since they do not specify the non-curl-free part of the Helmholtz decomposition of the vector field P in the matter at all. We can compare the divergence equation of the polarization with the fundamental equation of electrostatic in a vacuum, stating that the electric charge density ρ at a given point in space divided by the vacuum permittivity ε0 is equal to the divergence of the electric field strength E at that point. This comparison shows that the polarization volume charge density ρP is the source of the electric field in a polarized dielectric with the polarization P, just as the volume density ρ of electric charges is the source of the electric field E in a vacuum. It follows from these findings that the polarization in dielectrics must be taken into account in the equations of electrostatics derived from the condition where the electric charge is only present in conductors or in a vacuum. In order to describe the more general cases in electrostatics where insulating matter may be present in an electric field, we need to include the description of polarization in the fundamental equation of electrostatics.